Okay, welcome back to EE210B. So we are going to continue our discussions of inference over networks. Last time, in the last lecture, I derived a general expression for you that will help us characterize the performance of distributed algorithms over networks. I'm going to review that part quickly, and then I'm going to derive a simpler expression for that result, which will be very useful for us for the remaining lecture and lectures in this course, okay? So I understand that the last 4 lectures were the most demanding so far. That's because of the nature of the problem, right? These networks, because of the coupling that you have among the agents, because of the randomness of the gradient noise model, because of the nonlinearity in the update equations of the distributed algorithms, that makes the problem a little bit challenging, okay? However, this is your opportunity to see why this problem is demanding, right? To understand these derivations so that if you want to contribute to this area, then you will be better prepared to do so, right? So that you can understand what has been done before you. I could have easily skipped this part, just stated the theorems for you, right? But being advanced graduate students, you want to know more. So that's why I spend time doing this, okay? So now, let's continue, okay? Again, this lecture is based on the material in chapter 11, which we are going to conclude today, okay? This is just reminding you what we did last time. So remember that last time I introduced the notation H sub k to denote the Hessian matrix of the individual cost at the Pareto solution. This is our notation, right? And then I introduced G sub k to denote the Hessian matrix for the extended noise vector, right? The extended gradient noise vector in steady state, right? We called it S sub k sub E, right? This noise vector here at agent k at time I, and then the covariance of that, right? This times the star of that. As I goes to infinity, we assume that that covariance goes to RSK, and then if you replace the star by T, it goes to RQK. So if you put them together, you get this 2M by 2M matrix, right? So I'm just reminding you that H is the covariance, G sub K is the gradient noise covariance matrix in steady state. And for example, for mean square error costs and for the logistic regression cost and a few other costs, you can evaluate explicitly what these quantities are. And our expressions will depend on these quantities. That's why I'm revising them. I'm reviewing them here, okay? And then the main theorem that I proved last time was the following theorem, right? So I'm running the distributed diffusion or consensus algorithm, right? The general form of the distributed algorithm that I showed you before with 3 combination matrices A0, A1, A2, which includes many, many algorithms as special cases, including the non-cooperative version, diffusion, ATC, CTA, consensus, and so forth, right? So what I showed last time was this. Remember that this gamma, okay, comes from a condition, a smoothness condition on the covariance matrix of the gradient noise process, right? We said, let's assume that the gradient noise process, which has covariance matrix R sub S, let's assume that this covariance matrix, when I'm close to the optimal solution, it is smooth enough. Okay, satisfies a Lipschitz type condition, where on the right-hand side you had delta W to the power gamma, and this gamma could be something between 0 and 4. Okay, and for example, for quadratic costs, gamma will be 2. For other costs, it could be something else. So define this gamma M, which is the minimum between 1 and gamma scaled by 1/2. The important thing for us is that this is a positive number. That's what matters, okay? So what we showed last time was that if you compute this steady state variance quantity, so this is the variance at agent K extended, that's why I divide by 2, right? And to get the MSD expression, what I need to do, as I explained last time, right, you scale by mu and then take the limit as mu goes to 0, right? That will extract this part, which is first order in mu, and throw away the higher order terms, right? This gamma M is larger than 0, so this is a higher order power in mu. You understand that? So last time I proved these results. So this is the mean square error quantity at agent K, and this is over the entire network. right? This is W tilde I, this is W tilde K. That's why I divide by N here. And the difference, you have a J here. This J is a diagonal matrix which has the identity matrix at location K and 0 everywhere else. To extract that portion of this matrix X here, that corresponds to agent K. And what was this matrix X? I gave you several characterizations for this matrix X last time. Okay? One of them was in terms of the solution to a Lyapunov equation, okay, where Y and B are quantities that we know in terms of combination policies and the Hessian matrices and the G sub K matrices, right? Here it is. So this is Y, equation 54, right? In terms of the matrix X, S, which contains the covariance matrices of gradient noise, and this is B, right? This matrix F will come up also, which is the Kronecker product of B with B. The important thing is that the quantities that we have here, they all come from the problem definition, right? The step size matrix, the combination policies, the first equation, step size matrix, the second equation, the diagonal matrix of Hessian matrices, the third equation, and so forth, okay? So the X satisfies the Lyapunov equation in terms of B and Y. And I showed you last time that actually you can solve for this X in many ways. One of them, you can write it as a series, right, which is the first form, because this B is a stable matrix for small step sizes. So this is telling you what X is. Once you have X, you have that expression trace of X or trace of JX, right? So you can get the MST expression from it. But of course, this is still computationally demanding. We are going to derive a simpler expression later today. And these are other ways to express X. For example, this is the vectorized version of X in terms of the matrix F, which was the Kronecker product of B with itself, right? Because I showed you that the solution to a Lyapunov equation is essentially the solution to a linear system of equations, right? Which you get by vectorizing both sides. That leads to the second equation. We also have a closed form expression for the trace of X and for the trace of JX, which are the quantities you need in the expressions I showed you, right? This is what we derived last time, remember? In addition to this, we also derived at what rate the algorithm is approaching the steady state region, right, in terms of the smallest eigenvalue of the weighted sum of the Hessian matrices. You remember all of this? Okay? Very good. So this is what we proved last time. So what is it that I'm going to do today? Okay, what I'm going to do today in the first part of the lecture, I'm going to take this expression here. Remember, what are we interested in? I'm interested in the MSD, right, of the agent. What was the definition of the MSD? We say we divide this by mu, the step size, take the limit as mu goes to 0, that will eliminate this part. This part I showed you last time, it is first order in mu, I showed you this last time. So this part here, okay, the constant part of it will stay, because when you divide by mu, it becomes a constant. Then you multiply by mu again, you recover the MSD, right? That was the definition of the MSD. So this term here is the MSD that I'm interested in, right? The first order term is the MSD, okay? And last time I also talked about the excess risk measure. Okay, the excess risk had an expression similar to this, except that it was a weighted norm here, a weighted norm. So if you follow a similar expression, I will show you the result later. You will get something very similar, except that that weight, which involved the Hessian matrices, will also appear in the expressions. That's all. Okay, so whatever I say for the MSD will also apply for the excess risk. Let's continue with the MSD for now. So what I want to do now is this. This expression is fine, but can I simplify it? So now, the way I'm going to simplify it, of course, J is simple, right? J is just a diagonal matrix with mostly zeros on it. But let's look at X. If you look at X, okay, we have several expressions for X here. Okay, so here, this quantity is the trace of JX. It involves the inner product between B vec of Y, which is a quantity we know. It depends on the combination policies M and S, okay? B vec of J, this is a quantity we know. It is a big vector which contains zeros and ones. And in the middle, you have I minus F inverse. Now, if you remember, 2 lectures ago, I derived an approximate expression for this, which I'm going to use today. I showed 2 lectures ago that this quantity here, you can write it as a low rank matrix plus a higher order term in mu. Okay? Remember, this F has mu in it because F is B chronicle B, right? B star B transpose chronicle B, right? I'm just being convenient, okay? And B has M in it, okay? So this F has M in it, okay? So in the lemma I proved before, which I'm going to review with you, I showed that this quantity can be written as a low rank matrix plus a correction term that's higher order in mu, okay? So I'm going to replace that by that low rank term plus something which is higher order in mu. The higher order term in mu will join it with the others, right? And then, okay, so this is what I'm going to show. Okay, so let me be more explicit, okay? Okay, so let me go directly to the result, which is this. Sorry, not higher order in mu, a constant, okay? Constant, sorry, okay? We showed this 2 lectures ago. Okay, I showed you this result. You can go back. This is what I showed. I showed that I minus F inverse can be written as follows. You see, P chronicle P, what's that? A vector, correct? What is P chronicle P? You take each entry of P, you multiply by the vector P, right? And then you put all of them. So this is actually P chronicle P is a tall vector. 1 chronicle 1 is also a tall vector, and that's transposed, right? So what you have here actually is a rank 1 matrix. Okay, chronicle, the inverse of a positive definite matrix. Okay, because this Z here is symmetric. Sorry, no, this Z. Well, this is the definition of Z here. Okay, the H's, these H's here, they are Hessian matrices. They are Hermitian. Okay, they are Hermitian. Okay, this Z is invertible because the sum of the QHK is strictly positive. Remember I told you this last time, the sum of QK, HK is strictly positive. Okay. Now, plus a term which is of the order of 1. Okay, of the order of 1. Okay. Now, remember that this Q has mu in it, right? Has mu in it. Correct? It is proportional to the step size, okay? So this is the inverse here has terms of the order of 1 over mu, okay? Have terms of the order of 1 over mu, okay? So if you come back to the expression, okay, this Y has a product of m's in it. So this is of the order of mu squared. This quantity has something of the order of 1 over mu in it, which we already know from another result, right? So that's why this is first order in mu. So that we know, correct? So now, when I replace this by the low rank expression plus something of the order of 1, right? So I'm going to replace this quantity here by some low rank expression. Let's just write any arbitrary notation for now. Let's say R plus something of the order of 1, correct? So you will end up having this inner product times R times that, plus this inner product times a term of the order of 1 times that. So what would be the size of this correction term? It would be of the order of mu squared, correct? Which is small compared to mu, right? So that's what I'm going to do now. I'm going to replace R minus inverse by that R. Okay, the error, I blended into the last term, which is of the order of mu to the 1 plus gamma. So it stays of that order essentially when it dominates the mu squared, right? Okay, so let's continue. Okay, so before I get there, I need to remind you of this other result regarding also Lyapunov equations. This is the continuous time Lyapunov equation. Last time I talked about, you see there are there is this form here, for example, A x A star equals Q. This is the discrete time version, okay? Also sometimes called just time equation, okay? For this one, the product of the eigenvalues, pairwise eigenvalues of A and A star has to be different from 1 for it to have a unique solution, okay? And if Q is Hermitian and non-negative definite, this X will be Hermitian and non-negative definite, okay? In our case, this A is a stable matrix. So we encountered this type of Lyapunov equations last time. Today I'm going to encounter this other type of also called Lyapunov equation, or sometimes it's called the Sylvester equation to distinguish it from this, okay? In this particular case, X will be unique if the sum of pairwise eigenvalues is different from 0, okay? So the condition is different, okay? Here you need 1 minus the product of eigenvalues is different from 0. Here it is the sum, okay? And in our case, this will hold. And when this equation will come up, then the X that solves it will be unique. I'm going to show you, okay? Because this condition for the uniqueness of the solution will be satisfied, okay? And the solution, when A is stable, what does it mean for A to be stable in the continuous case? The eigenvalues are in the left half plane, okay? It's a different condition than here. Here, A being stable means the eigenvalues are inside the unit cell. So when A is stable, this X will be Hermitian and non-negative definite, okay? So this is a review of what we talked about when we discussed Lyapunov equations back, many lectures ago. The proof of this is in the notes. You can go to the appendix, you will find the proof for these facts, okay? Okay. So let's come back to our result. So this is what I would like to show. I showed you earlier in the previous theorem that the lim sup of the variance of the error, expected value of W tilde Ki squared, is trace of Jx, correct? Plus a higher order term in mu. I'm going to show now that the trace of Jx, I can write it like this. Because the higher order terms, all of those will disappear, right? After you use that expression to compute the MSD, which is divide by mu, take the limit as mu goes to 0, right? And multiply by mu again. All the higher order terms in mu will disappear. What will be left is this. And this is what I wanted you to see. Remember, I told you last time that I'm going to take this trace of Jx and express it as combinations involving what? Involving the p's. The p's appear inside the q's, remember? These q's are defined in terms of the entries of the Perron eigenvector, right? A2p times the diagonal matrix involving the eigenvalues. These are the entries of Q, correct? So the P's are there, the H's are there, the G's are there. Okay, so this is a much more convenient expression to use. Okay, much more convenient, and we are going to use it in many examples later today and in future lectures. Okay, fine so far? Now, in the general complex case, this H is 2, this H sub k is 2m by 2m. This G sub k is 2m by 2m, okay? Observe I have an inverse here, but this matrix is positive definite, so it's invertible, okay? Now, in the real case, this H will be 1. Little h will be 1, capital H will be m by m, and this G here will be R, right? R S K. You can be explicit in that case, right? Because this G was 2m by 2m, R S K, R Q, and then the transposes and the complex conjugates, right? So in the real case, I think I have a slide here showing how the result will look like. So, right? So H is 1. You use RSK instead of G, right? This is just. And I also wrote down what the convergence rate is. The convergence rate is already written in terms of Q and H's, so I don't have to do anything there. You see? So you're going to see how useful this expression is that you are seeing in this lemma and in the previous general case. Many results you can get as special cases from this expression. For example, I'm going to show you these things. For example, LMS is a network with a single agent, right? So N is 1. N is 1, okay? So if you write down what H is for a single agent, what RSK is for a single agent, what Q is, this is exactly the MSD performance expression we have for LMS. Okay, if you remember, mu sigma V squared times M over 2, or depends how you define mu, with 2 mu or mu in the update. This is the generalization of the famous expression that you have for the performance of single agents that we derived in the first part of this course. In the first part of this course, I derived the expression, I believe it was something like mu trace of H inverse R or something like that. This is the extension to n agents. And it includes that as a special case. So this is the natural extension of the performance for single agents to multiple agents, and includes results, for example, for LMS as a special case. You understand? Okay, so let's prove it. Okay, so now is the derivation. Okay, the derivation is not very difficult. It involves some algebra using properties of Kronecker products. Okay, so what do I have to do? You see, I have to take what I have here. Remember, this is the trace of Jx. I told you that the trace of Jx has an expression, right? And this was the expression given in the lemma. I multiply by mu, take the limit as mu go to 0, and then put the mu back. When I do this, the result should be the MSD that I'm looking for, right? I'm just writing the definition in this equation, right? It looks long, but that's just the definition, correct? So what I have to do now, I would like to find out what this expression is. Okay, what this expression is. You see that I already removed the higher order term mu to the power 1 plus gamma because it will disappear when you do these calculations, right? Another term will disappear when I do these calculations when I replace the I minus f inverse by the approximation I'm going to do. That higher order term, the mu squared, will also disappear, okay? So let's take I minus f inverse and replace it by the low rank expression. What was the low rank expression? Here it is, okay? So I'm writing it down here, okay? And the O of 1 becomes O of mu squared y, because that O of 1 is multiplied by the y, correct? B vec of y, which has m squared in it. Understood so far? So all I did here, I used the result of the lemma to write down what I minus f inverse is, correct? So now let's simplify. All I have to do now is to show you that this expression in the second line, right, essentially gives you that, correct? I have to do that algebra. Okay, so this is now just algebra. Okay, so let's look at it slowly, you see. 1 transpose Kronecker I, what would that be? It would be many i's next to each other, correct? The second one also many i's close to each other. And then when you compute the Kronecker products of these two matrices, you will get many identity matrices. You just spell it out. So you will get a matrix that has many identity matrices and then multiplied by a big vector that has many zeros, okay? And by the way, this is a block vector, okay? Block vectorization, right? So if you do this calculation, right, this is very simple. These last three terms, they all involve identities and zeros, right? Very easy for you to check that these last three terms, you get the vector, which is the vec of the identity. Okay, remember this identity has ones on the diagonal, right? So what's the vec of the identity? 1 all zeros, that's the first column, and then the second column, okay, fine. Now, I just want to tell you one thing, okay? When we talk about, if I have a matrix X, and I talk about B vec of X, so what's the definition of B vec of X? You think of X as being a block matrix, right? Let's say 3 by 3 blocks, correct? And then you vectorize each block. So you vectorize this block, you get a column. Then this block, you get a column, and then, okay. Now, the result of the B vec depends on the size of the block, right? I can take a big X and divide it into blocks of size m by m, or 2m by 2m, or 3m by 3m. The corresponding B vec depends on how I partition this matrix, right? Right, okay. Now, if my X happens to be 2m by 2m, happens to be a single block of size 2m by 2m, and I want to compute B vecs of size 2m by 2m, because these B vecs, these vector Kronecker products here are relative to blocks of size 2m by 2m. If my matrix happens to be 2m by 2m, how is the B vec of that matrix different from the vec of that matrix? It is the same. right? So if the matrix happens to be the size of the block, there is no difference between VEC and BVEC. That's why you will see sometime, because this quantity here, okay, the result is a vector of size, is a vector corresponding to a matrix of size 2m. Okay, so this will give rise to a matrix of size 2m by 2m. For that matrix, I will use BVEC or VEC interchangeably because of this. Okay, fine. So look, so what I showed here, by the way, this is just algebra. You just can write it down and you will find out this is what you get, okay? So the product of these three quantities is what? The vector corresponding to the identity matrix of size 2m. Okay, so what comes next? Next, I have to compute Z inverse times that. Right? So let's find out what Z inverse times that is. This Z inverse here. So here it is. I have to compute this quantity, correct? So let's find out what this quantity is. This quantity is a vector because it is a matrix times a vector, correct? Okay. So Z is an invertible matrix. So obviously this, if I write down this as the linear system of equations, this linear system of equations has a unique solution, correct? Okay. So the x that I'm looking for is the unique solution to that linear system of equations. But I know what Z is. Okay, so I'm trying to find out what this x is. So this is how I'm going to do it. Let's replace Z by the expression. What is Z? Z is the sum. Q times the Kronecker product involving H's, Q times the Kronecker product involving H transpose. That's how we define Z. This is just definition. So write down Z. You will get this sum times X, this sum times X equals VEC of phi on the right-hand side, correct? But now remember this property of Kronecker products. The VEC of ABC is equal to what? It is the VEC of, sorry, not VEC, right? It is C transpose, by now you know this by heart, right? Kronecker A, VEC of B, correct? So look here, okay? Here you have a matrix, Kronecker, another matrix times a vector, correct? So this little x is a vector. What's the size of this little x? Anyway, if I take this vector and I unvec it, let me ask you the question like this. If I unvec x, I will get a matrix, correct? What will be the size of that matrix? Okay, you see, okay, let's look at it in a different way here. VEC of the identity of size 2m. What's the size of that vector? The square of 2m, correct? So this x has the same size, correct? So if you unvec it, you will get a matrix of size 2m by 2m, right? So x is a matrix of the size of the block, correct? Okay? So X is the matrix version of the vector X, is the unvec of X. So you see here, I can apply this property here, right? I can apply this property here and write that what I have, this product here of these three terms is the vec of what? Is the vec of X in the middle, identity here, HK here. Correct? The vec of this will be I transpose Kronecker H times the vec of capital X, which is little x, correct? Okay. And here also, I'm going to get the vec of I X HK, correct? Of course, you have a sum of QKs, and here you have a sum of QKs, correct? All of this equals to the vec of I on the other side, correct? But now, I can remove these i's. I don't need these i's, right? Let's remove the vec. What do you get? You get a vector equation now. If you remove the vec, you will get the sum of Q times H here, the sum of QK times H times x, correct? Plus, on this side, I'll get x times the sum of qk's times h's equal to I, correct? So this is what, of course, here I'm just reminding you of the property and the definition of x. Okay, what I wrote there is exactly this. Okay, that this quantity is the vec of that, this quantity is the vec of that. When I remove the vec, I end up with this equation. What kind of equation is this? Sylvester, right? The continuous time Lyapunov equation. And the A is this sum, which is positive definite, right? And I needed the eigenvalue of this plus the eigenvalue of that to be different from 0, which will be different from 0. So it has a unique solution, right? I can guess the solution. It's not always the case you can guess a solution. Since it has a unique solution, if I find one, that's the solution, correct? Okay, so I'm saying the solution is 1/2 the sum, right? You cannot argue with that, because if you substitute this x there, you get identity. It's not, this is not always the case, okay? In this case, it's trivial. Fine? So I found my little x. What is my little x? The vec of this. Correct? Okay? Very good. So my x now, okay, there it is. It is the vec of that, okay? So this is a typo there, because if you go back, so I found that this is my little x, right? So here you see Kronecker b. This b I forgot to write it in the next equation. Okay, so here it is. So far, I was able to show that the first line is equal to the second line. So let's continue. Okay, because I want to show this goes to that expression that I showed you before. This is the higher order term, I'm just carrying it with me. So let's now compute this. Fine, are you following? Compute it. Here is it. It's just a sequence now of applying Kronecker product properties. That's it. So let me do it slowly so that you see it, okay? Here it is. Follow. Okay? So here the typo is still missing from the slides, okay? This is B here. This is B here, okay? Just, okay. So this is the expression, correct? Okay. So now this expression is an inner product, right? It's an inner product between this row vector and that quantity. And we have this property of, right, of Kronecker products, correct? Okay, so this quantity here, I can, okay, remember this property of Kronecker products? The trace of AB was something like this, vec of, or bvec or vec, whichever you decide to choose, okay? Transpose. So you vectorize them and then you compute the inner product of these two things. That's what the property says, correct? So you see here, I already have this as the B vec, so Y plays the role of B, correct? So here you see trace, and B is there, correct? So what is A? Okay, what is A? Okay, so A should be the unvectorized version of whatever comes next. So it is the unvectorized version, right, of whatever came next. I just wrote it down. Fine? I just wrote down the property, correct? Okay. Okay. So what is the unvectorized version of what I have here? Now I use the other property. You see, what is the vec, the B vec of A, B, C? It is C transpose Kronecker A, right, times what? B vec of B, correct? Okay. Now, so let's look here. Here I have B vec of x. Vec of x is the same as B vec of x because x is 2m by 2m. It's just one block. Okay? So this is x. Okay? So there it is. You see, so the m B vec of that, right? So, okay? So what I have here, is something written in the form that you have on the right-hand side. The ambivec of it, the matrix version of it, is ABC. Okay, so what is B? B is X. What is A? Right? A is what you have here. What is B? Is the transpose of what you have here. Right? You see? Just apply the properties slowly. Fine? Are you following? Okay. But now, the trace of AB is the same as the trace of BA. So all I did here, I took P Kronecker I to the right-hand side. So it's multiplying Y. Sorry, I took P Kronecker I times X to the right-hand side. Okay? You see here, P Kronecker I X, this P Kronecker I X, I took it to the right-hand side. Fine? And I replaced Y by what it is. Very good. Fine so far? But now, what is M times A2 times P? That's by definition Q. Right? Q. Okay? Because remember, for example, A2, just so that you know how this is done, A2 is A Kronecker I, correct? And then P Kronecker I. Right? So this will end up giving you A2P Kronecker I. And then if you repeat for the M will come in here. So you end up getting Q Kronecker I. On the other side also you have A2, so you'll get Q Kronecker I. What's left? S. What is S? A block diagonal matrix with the G's, correct? So let's look at this now. Okay. Sorry, okay. What was X? Remember, so this is the trace of something times X. I can write it as the trace of X times something. Nothing changes. So I put X first because I already know X. X is 1/2 of that. So that's X. What is this quantity here? You know, what is Q Kronecker I? Q Kronecker I is Q1, Q2, Q3, each one of them multiplied by I, right? It's a tall vector with Q's. And this is a row vector with Q's, right? And this is a block diagonal matrix sitting in the middle, G1, G2, G3. So when you multiply Q's by this block diagonal matrix by the Q's here, what do you get? And that's the result. You see? Nice, right? Very compact expression, okay, that we get for the performance. So this is what I wanted to prove, correct?
Actually, would it be Q transpose GKQ?
No, QK is a scalar, right? QK is a scalar. Okay? When you do Q Kronecker I, it becomes each little Q multiplied by an I. You understand? Okay, so these Q's are scalars here, okay? Very good. So there it is. We derived what we wanted, correct? And this term will cancel when you do the limits. Okay? So I'm reminding you of the expression. This is the expression. Now, what's interesting about this expression? Okay? So this expression is the MSD for node K. For each node K, this is the MSD. But if you look on the right-hand side, it's independent of K. On the right-hand side, this expression, you see, you are adding over K. For each K, what you have on the right-hand side is the same quantity that you compute for each agent K, right? All of them will end up having the same performance. You understand? For every agent K, the performance of the distributed solution at agent K will be given by exactly the same expression. So the performance of all agents are equalized to first order in mu, right? To first order in mu. Higher order terms, there may be differences, but these differences will be of higher order. You understand the detail here? I'm not saying every single agent will have exactly the same performance as another agent. To first order in mu, yes. And if mu is very small, that's all you care about. But there might be small differences in higher order powers of mu. Now, to first order in mu, the average performance across the network, you add all of these, divide by n, you get the same thing, correct? So that's it. So these distributed algorithms, they are able to equalize performance across the agents, even though some agents may be noisier than others, right? Understand? Okay. Here I'm just repeating the result for the real case, okay? Good? Any questions so far? So that ends the theoretical part. Now I'm going to show you several examples, okay? So now, yes?
Why do we have that? Why is it the same meeting?
Because of the interactions, you see. It's true that I'm interacting only locally with my neighbors, but information that other agents have down there will end up reaching me, and this is a steady state performance. This is after sufficient time has elapsed, right? So information from each node will end up reaching each other node, right? And they end up equalizing their effect. It's because of the local cooperation and because this is a steady state performance. You have given them enough time to learn from talking to each other, okay, which is an interesting effect, okay. Fine. So now let's do some examples. Now the rest of this lecture are several examples, okay, several examples. I may have time to cover all of them. I may not have time to cover them. If I don't have time, you can read them. These are just solved examples in your notes, okay. So let's specialize these results to consensus and diffusion. The result I derived for you is very general, right? It assumes 3 levels of combination policies, A0, A1, A2, just because I want the result to cover many strategies as special cases. In particular, for example, if you set any 2 of them to the identity and the remaining one to some left or doubly stochastic matrix A, that will give you either consensus or diffusion, ATC or CTA, right? Understood? Very good. So in this case, what would be the Qs? So let's see if you are following. In this case, what would these Qs be? Because they appear in the performance. Each Q, right? Because remember, each Q is A2P times the mu's, right? This is the vector Q. Pick any one of these. Let's say ATC. This P is the Perron vector for the product of the A's. The product of the A's will be A itself, which happens to be A2. So this is P. So each QK is simply mu K, PK. The same thing will hold for the other 2. Try it and you will see, right? So when you set only one of them to A and the other 2 to the identity, you can replace the Q, right? You can there is no A2 anymore in the definition. You just replace the Q by the step size times P, correct? Okay. And what's this P? P is now the eigenvector that corresponds to this A, because A will be the product of the A's, right? Understood? So P is the Perron vector, right? And we talked a lot about the Perron vector in an earlier lecture and why it's important. Here you see that it's very important for performance. We talked about it before, how it determines where the network is going to. Here we see that it also determines how close you get to that limit point. They are all positive because your network is strongly connected, right? They add up to 1 by definition. The Q will be that. So now if you replace this Q into your expression, what do you get? Here we used to have QK, correct? So that's it. This is the convergence rate. So all these algorithms will essentially converge at the same rate given by this expression, right? Okay, so this is the distributed rate of convergence. And the performance, okay? Now, these are examples. So I'm showing you special cases. Okay, so for example, here, what would have appeared here? QK, correct? You would have, so let me see, what's the first case that I'm discussing? So I'm discussing the case, okay, where the step sizes are uniform. Fine? Okay. Where do I say that? I'm looking for it. Oh, here, sorry, yes, that's why the P's disappeared, okay? Now, when A is doubly stochastic, what would be each P? 1 over n, correct? So come here. Here you should get mu 1 over n, correct? And here you should get mu squared 1 over n squared, correct? So now, what did you say? No, I'm saying multiplying the h here, right? And multiplying the g. So you can see one of these mu's comes out, one of these n's comes out, right? And then you get the sum of h, the sum of g there, right? You understand? So that's what you get in the doubly stochastic case, right? And uniform step sizes. And the convergence rate, because I had the sum of, here I had mu p is 1 over n, correct? Now, if you are paying attention, we saw this expression before. These were the expressions that match the performance of the centralized solution. This was the performance, the MSD performance for the centralized solution, where all agents send their data to a central processor that runs a centralized stochastic gradient algorithm. So what this is saying is a network running a distributed algorithm where agents only have access to local information, not to the entire information, can match the solution of a centralized implementation, right? If you give them enough time to learn, yes.
Was it the same convergence rate?
Yes, the same. Okay, we are going to see here. Okay. Well, the expressions are going to come up, okay? I don't remember now the exact expression, but they are going to come up, okay? You understand? This is an interesting conclusion, right? Just by talking locally, if I give the network enough time to learn, they will perform as well as having a powerful central processor doing all the calculations for them, right? For a doubly stochastic performance. Fine?
We inferred this alpha from the long-term dynamic model, right? So I get this thing about convergence rate and...
Right, but remember, I told you that the evolution of the long-term model, right, it is evolving very close to the, or for large enough time, okay? So this is not the convergence rate from time zero. This is the convergence rate once you got close to the convergence region, how fast you are getting, okay? This is convergence rate at that stage. Do you understand? Okay? Yes.
But how do we know that that point, the point that this is valid onwards, has already converged? Maybe, right, maybe it's already the steady state.
Right, okay.
How do we know how
Right, no, that's a good question. We have quantified these different stages of convergence rather precisely in another type of work that we have, okay, which will take longer to deduce here, okay? If you are interested, I can give you the references. Actually, these articles just appeared in the Transactions on Information Theory, where we show, okay, we show starting from time zero, okay, starting from time zero, your network, okay, has 3 well-defined stages of convergence, okay? The initial stage, this initial stage here, depends on the second largest eigenvalue of A. I'm just stating results now. I'm not proving it. The proof requires some arguments. You can find them in the reference, okay? You can go to my website. The papers are on the website. The links to the papers are on the website, okay? The second here, okay, is the convergence rate that is centralized. Well, the centralized there, what we mean by it is the following, okay? Assume you have the average of the estimates across the network, right? That's a dynamic system. Study how well that average is converging. If you remember, when we transformed our evolution equation into W hat and W check, the W hat actually had that interpretation. This is one of your homework problems. The evolution of W hat corresponds to the evolution of the average estimate across the network. The rate at which that is converging is the second rate of convergence. And the third rate of convergence is this one, okay? So you can be more explicit about how the network is actually converging to steady state. There are 3 well-characterized regions of convergence, okay? Here I'm only talking about this last one, okay, because I use the long-term model. To characterize these other two, the argument becomes a little bit more involved. It is doable, but it's a little bit more involved, okay? Let's continue, okay? So here we see that consensus and diffusion are able to equalize the MSD performance. We just said it, okay? Okay? Very good. Now, let's look at another example. This is mean-square error costs, okay? Mean-square error costs, okay? So the previous example, it was general, right? General H, general G, general costs, J sub K with Hessian matrices H and gradient noise covariance G. Here, let's go back to the mean-square error network. Remember that network? Each agent is receiving a stream of data D and U, scalar D, U regression data. So this is a quadratic cost that satisfy a linear model, right? And they are working together to estimate that linear model WO. Let's assume in this first example, case 1, okay, that all the step sizes are the same across the agents. The covariances are the same across the agents, right? Let's just assume this case. So the Hessian, so this RU in this case is related to the HK, right? This is saying all the H's are uniform across the agent, right? What is HK in this case? RU transpose in the complex case. Remember, RU transpose. But regardless, it is the same, okay? So now, and what is the covariance of the noise? The covariance of the noise, okay, we did this in a previous example early on. We found out that the covariance of the noise for the mean square error cost is given by the noise variance. This is the measurement noise variance at each node, right? D is UWO plus noise times the covariance. Fine? We did this some time ago. I'm just repeating it. So, if you write down what the Hessian matrix is in the quadratic case, it's block diagonal with RU transpose, so it will be uniform. Okay, what about the covariance G? Okay, remember that G has two moments in it, right? Okay, two moments in it. One, you construct from the expected value of S star. The other, you construct from S transpose. In this case, I know what SS star is, and if you remember the way G was constructed, okay, so this is RS, and this is RS transpose. I still need the expected value of SS transpose, right? I don't know that in this case, so I'm just calling it an X, and it doesn't matter in this case. Why? It doesn't matter because in the expressions you have trace of the sum of H inverse. The sum of H inverse in this case will be block diagonal times the sum of the G's. The sum of the G's will not be block diagonal. But when you multiply the block diagonal matrix inverted, it's still block diagonal times the G, and take the trace of that, only these block diagonal terms will contribute. I don't care what the X is, right? These will disappear. You understand? Okay, okay. So if you do that calculation here, okay, so let's do it here, okay? So what was the expression? Just so that you remember, it was something like 1 over 2H, correct? Let's do it slowly. This time, in the future examples, I will just tell you, if you do these calculations, this is what you get, okay? So that you see it at least once. It was something like this. The trace of what? The sum of mu k. What's mu in this case? I think it is a constant mu, right? So let's keep it constant. Constant mu times pk times hk, correct? Which is h in this case. Inverse. Times the sum of mu squared pk squared gk, correct? Okay. Now look, this h is a constant. So it comes out of that sum, right? So here I will end, and this mu and that mu squared, I end up getting here mu over 2h, correct? Trace of the sum of pk inverse times h inverse, right? Times the sum of pk squared gk, correct? Very good. Okay? Trace of that. Now, this H inverse here, I can bring it in that second sum. Okay? So I'm going to remove this H inverse from here, put it inside this sum here, right? Okay, so let me clean that up. Okay, sorry. Sum of pk squared H inverse, right? What is this sum here? By definition, it is 1, right? We normalize the, okay? So I can remove this sum. So it is the trace of this thing that I have to compute, correct? So now, if you take H inverse and multiply it by G, what do you get? You will get sigma Vk squared I, right? Okay, I something something, correct? Okay, multiplied by pk squared, and then the trace of that. What is the trace of this? Okay, this is a sum. What is the trace of each one of these? No? 2m. 2m times pk squared sigma v squared, right? Okay, so the trace of that will be, so I'm going to get, if I go back here, I'm going to get 2m mu over 2h, right? Trace, okay, which will end up being the sum of the pk squared sigma vk squared, correct? Okay, so this is what you have here. Remember, this h is 2 for complex, right? So 2 and okay, you get this. That's how you get these expressions, right? You just have to do it slowly. Okay? I will not do it again. You will believe me from now on. Fine? Okay? So here it is. Okay? So this is the performance of the distributed solution. Now, if A happens to be doubly stochastic, what will change? You will get 1 over n squared out. This is exactly the performance of the centralized solution for the mean square error estimation problem. Again, you see that repeated here, right? Okay. So in the case of the network, you end up with a weighted sum of the noise variances. If the network happens to be doubly stochastic, that weighted sum replaces the pk squared by 1 over n squared, so you recover again the performance of the centralized solution. Remember that when we talked about the centralized solution, we showed that the performance of the centralized solution is better than the average performance of the non-cooperative solution. If you have n agents and you average their performance, what do you get? You get mu m over n, the sum of sigma v squared. In the centralized case, you get mu m over n squared, this, right? So you get an n factor improvement in that case. Right, so we showed there that the centralized solution is better than the non-cooperative solution, the average non-cooperative solution, by a factor n. The same thing here, right? If this is doubly stochastic, the expression is the same as the centralized. So the same conclusion holds here. So cooperation in this case helps, right? If the agents solve the problem on their own, you get mu m over n, right? The sum of the sigma v squared. If they cooperate through a doubly stochastic combination policy, you're going to get n squared, so n times better, just like the centralized solution. Number one. Number two, just like the centralized solution, this doesn't mean that the network performance, that every agent will perform better than every individual non-cooperative agent. Are you following what I'm saying? Okay. So maybe let's move a little bit slower. So here it is, okay? If my matrix is doubly stochastic, this is the performance of the distributed solution. Fine? This is exactly the performance of the centralized solution we derived before. So conclusion number one, the distributed network can match the performance of the centralized solution if you use a doubly stochastic matrix, correct? So that's a useful conclusion, that only through local processing I can do as well as having this powerful brain doing the calculations for me. Number one. Number two, Number 2, what is the performance of the non-cooperative solution? Let me see if I have it here, otherwise I'm going to write it down. What was the performance of the non-cooperative solution? The average. It was mu m over 2 times the average. Correct? If you average the performance across n independent agents, this is what you get, because each one of them is mu times m times sigma v squared, right? So you see that the distributed solution, just like the centralized solution, is n times better, right? But this doesn't mean that if I have n independent non-cooperative agents, each one is performing like this, correct? At this level. Individually. And now I come and connect them by a network, doubly stochastic network. Each one of them now will perform individually like this. Correct? Okay? I showed you before examples. I can pick the sigma v's such that it's not necessarily the case that this will always be better than the best there. Right? So on average, you do as well as the centralized. On average, you do better than the non-cooperative, but it doesn't necessarily follow that individually every agent will attain better performance. As a group, they will attain better performance. That's why this is called a cooperative network. As a group, we will do better. But individually, some of them may have to pay a price for doing this. Okay? You remember this. I gave an example before. I just go back to these numbers I gave you before and they will work out. Okay. Let's go to the next step. What if A is not doubly stochastic? When A was doubly stochastic, those P's disappeared because they become 1 over n, right? When A is not doubly stochastic, if you go into your expressions, the P's will be there. So this is the performance, right? When A is not doubly stochastic, right? So you have now weighting in terms of these Perron entries, okay? And this is also for the general case where the mu's are not uniform. Otherwise, if mu were uniform, this sum here can disappear, okay? Very good. So let's do some examples, further examples. So this is the general expression. There are some cases where I know what this P is. For example, for doubly stochastic, I know what this P is. There is another A for it. This A, which is common, the uniform or averaging rule. This is a common rule. What this rule says, if I'm a network, I have 3 neighbors, including me. I'm going to assign to each one of them 1/3. You have 4 neighbors, 1/4. So each agent weighs equally its neighbors. That's what the uniform rule is. I just average the information from my neighbors. Okay? So it's defined like this. Okay? So this is the weight that agent K assigns to information arriving from L. So I'm agent K, I'm assigning the information. So it should be 1 over the number of neighbors I have, right? 1 over NK. So NK is the degree, right? So it is the size, the cardinality, how many neighbors I have, right? This is just notation, right? Now, for this matrix, you can find in closed form what the entries of P are. If you write down this A, you can find what the eigenvector P is that corresponds to the eigenvalue at 1 in closed form, okay? So this is what the expression is. You can check it. This is not difficult to check. This is what the expression is. This vector P will be like this. This is the degree of node 1, the degree of node 2, the degree of node 3. So it's the vector of degrees normalized by their sum so that they add up to 1. That's what P is. For the uniform rule, the eigenvector P, so for the uniform rule, what this is saying, the relevance of each node is how many neighbors you have. The more neighbors you have, the more P you have. That's what this is saying, right? In the uniform rule. Okay, you have access to more neighbors, okay? So in that case, if you go back, replace P by this, the expression becomes this, right? So the noises are weighted by how many neighbors you have, okay? I'm just showing you expressions now, right? How the expressions simplify, you know? So this is interesting if you look at it, you know, after all this trouble we went through, right? A few lectures, and you were patient enough to survive to this point, right? You get a beautiful expression like this. You know, what does this say? I give you a network. I don't care how many nodes it has. N nodes, 1,000 nodes. Okay? I define a random topology over this network. Okay? Random topology over this network. And now I tell you this. This network is going to run, let's say, diffusion to solve an estimation problem using the averaging rule. Tell me what performance you can expect from it. Very neat expression, right? All you have to do is know how many neighbors each one has, how much noise, right? That's it. This is the expression, okay? And you can see this collapses to the case where you have a single agent, right? There is just a single agent. This is not there, just a single agent. This is not there, sigma v squared, right? So this is a generalized expression. Of course, this is already a special case of a more general expression, okay? So there it is. Okay. So let's look at another example. Okay, another example. Just some things changed from example to example. Okay, I don't remember now what changed in this example. Let's see what changed in this example. Okay, so in this case, the H is not uniform. Right, I'm assuming that the covariance is diagonal, but this K, sigma U, K change. So technically, it means that the H's are not uniform across the agents, okay? Just to show you different examples, okay? So in this particular case, of course, here RU, I put it out. RU transpose, I put it out. Again, you have the X's because you don't know them, okay? Now, if you plug this into the expressions, okay? So this is for the general case when I have left stochastic, right? If you have the P's there, it's because it's left stochastic. Otherwise, I would have replaced it by 1 over n, right? So that's the expression in this case that you will get if you do the calculations, right? So if I did not have, if the sigma u's were uniform across the agents, it would disappear. And you go back to the previous case, right? Because this appears under an inverse, this appears here, they would disappear. But if your agents have different regression power, they do not disappear. The performance depends on that as well. Okay? In the doubly stochastic case, you get this expression here. Okay? Okay, so you can study all these different cases. Okay? You get the point, right? Okay, I will not. Okay, so you get the point. I have many different cases here. And this is just a simulation to show you that the theoretical expressions that I'm showing you indeed match simulation. So what do? I take a network generated randomly. This is a code that generates a random network like this. In this case of size 20, you can tell it what size you want. And then it assigns random noise profile, random regression profile across these agents. And then it runs, for example, diffusion or consensus. It averages the learning curve and plots them. And then you compare the steady state, of course, averages over many experiments for small step sizes. You can also make the step sizes constant or change them across the agents. And you compare against the theoretical value, right? So, yes.
What do you mean, the regression profile?
The sigma u k squared, okay? This particular code allows you to use sigma uk uniform across the agents or different across the agent and so forth, okay? So it gives you plots like this. What this is saying for the 20 nodes, how the noise profile is. So for example, node 0 has this much noise, node 1 has much more noise, right? So you can see that some nodes are noisier than others. Noise 0 has much more signal, for example, than node 0 than node 5, right? Okay, so if you run these simulations, in this particular case, I tell you what the mu is, how many experiments I averaged, you get the point. What's the size of M? You get curves like this. Okay? The learning curves. Okay, now you see that this match very well with the theory, right? Right? Which is good.
Yeah, but
Yes.
So mu is 0.002, which is quite small.
No, I'm coming there. This is the next slide.
Okay.
Yeah, okay, I'm coming there. The results I proved were to show I derived the expressions for you, MSD expressions, that tell you this is the performance for sufficiently small step sizes to first order in mu. Okay? But before I go there, I just want you to look at this plot. You can see that if the step size is very small, good match between theory and practice. Okay, good match. Number one. And diffusion and consensus perform equally well, even though ATC diffusion, we can show analytically, we are going to show this later. You always have this additional improvement. Okay, in this case it is a small because the step sizes are small, but I'm going to show you an example where it becomes bigger. But analytically you can show that ATC diffusion always improves a little bit, okay, because you adapt first, you learn first, and then you combine. Like I told you the example before, first you think before you share information, right? So it does translate into something that you can show makes a difference. This simulation is showing it, okay? Now, what I do here, I enlarge the step size. It's now what, 50 times more, 10 times, 50 times more, or 20, whatever it is, multiples, right? More. So what do you see now? Okay. Okay. If you are paying attention, you should see many things in this plot, right? First of all, like she said, theory and simulations match. Very good. Number one. What else do you see? It continues. ATC diffusion continues to outperform, but now more, right? That's fine. Okay? Sorry? Right, but now my question to you is, what are these theoretical limits here? I only gave you one expression. Right. I only gave you one expression. I told you the MSD is this expression. How come I plotted two theoretical lines here, right? What do you mean same value? Come on. Yeah, right. No. It is, because this is not the expression from the lemma. This is another expression. Okay. This is a future expression. Okay. And that's what I'll explain to you later. Okay. Because remember what I did? Okay. What I did, okay, this is where this difference comes from. Trace of Jx, that was the performance expression that I am interested in. Right? Okay. Now, that trace of Jx, if you remember, x depends on b, right? So x has information in it about the algorithm structure because b depends on a, right? Depends on a0, a1, a2. Where a goes changes b, right? So that expression for the performance is a more accurate expression for the performance than the first order approximation I derived. Because how did I derive the first order approximation? I took that expression and wrote it down as something plus a higher order term in mu, and I threw that term away. If you keep it, you get a better approximation for the MSD, and that approximation will be now algorithm dependent because it depends on b through x, right? Okay, and so using that expression, I plot, and you can see that that expression indeed matches the theory. When mu is very small, the approximation that I did and the original expression will match very well because mu is very small. Mu squared and these higher order terms will really be very small, right? But for larger values of mu, then these higher order terms start interfering, right? Start interfering, and this result is showing it. You get the point? That's where this comes from. So that's why later in this lecture I will give you another expression to get more accurate expression evaluations of the MSD. The ones I gave you are perfectly fine. These are the ones that you will use most of the time because most of the time we are interested in first order approximations for small step sizes. But if you want to be more accurate, if you see something like this and you want to explain it, you have to know how to explain it, right? Okay. Yes. Yes.
So you have this value in mu and you have m and n, and this is an MSD network. You have the regressive covariance traces.
Yes.
Squared two and the noise variances as well. Well, if you just vary any of those parameters and keep mu constant, you're not necessarily going to see any of these properties like good match between simulation and theory, a gap between CTA and ATC. So you always have to consider what...
No, like I say, I'm going to show you later. Analytically, we can show that this is the case.
Sure.
Okay, we are going.
How big the gap is going to vary based on all the parameters?
It depends on the difference between your expressions, right? So you can find exactly what that gap is analytically because I have the performance for this case, I have the performance for this case. Just subtract the trace of Jx for both cases, right? So technically you can evaluate it if you want. That's how I did, by the way, these tables here. Okay, here, you see? These are the theoretical values that I get from these expressions, okay? And you compare them with the plots and they match perfectly well, okay? So what I'm saying, you have expressions that can tell you, you tell me what your parameters are, as long as the step size is small enough to ensure convergence, then these expressions will predict either to first order in mu or to higher accuracy what the performance is.
But this thing about sufficiently small mu, so
yes.
to vary the noise variances, the sufficiently small mu might have to be even.
Yes, of course. Yes, the value of mu depends on your actually not on the, it depends on the H's, right?
Yeah.
The mu's will mainly depend on the H's, on the Hessian matrices.
And we always find such a mu.
Yeah, that's the theorem we proved, that there exists a sufficiently small, right? This was one of the first theorems we proved. Okay, when I proved, remember I used the Gershgoring theorem arguments, right? I showed there that, right, the result of that theorem is that a sufficiently small and positive upper bound mu0 exists such that for every mu less than that, the algorithm is stable. Okay, so this is proven. Okay, it's a good question, right? But you have to prove it and it's proven. Okay, very good. Now, this keeps going, okay? So this comes back to that question I mentioned to you before. So is cooperation always beneficial, right? If I have non-cooperative agents, each agent will get this performance that you have here in the middle of the slide. If you average, that's what you have, 58, okay? And therefore, the distributed solution is 1 over n times that. If you are using doubly stochastic A, that's what I said before. But does it mean that every agent will do better than the non-cooperative agent? I showed you this example before. Here I'm just repeating it. If you do the calculation for this noise variance at agent 1, this noise variance at agent 2, for a case of 2 agents, you are going to see that the distributed performance is better for one agent but not better for the other. Okay, so the same conclusion we did before. Okay, so I'm going to skip this calculation. Okay. There is more. This is just another example. Okay, you can read it. Okay, it's not difficult. The difference between this example and the other is that now I assume that the different agents are seeing data that arise from different models, right? From different models. So in this case, the network will not go to any one of them. Will go to a Pareto solution, right? And in an earlier example, when we talked about Pareto solutions, we found an expression for the Pareto solution for this case. Okay, so in this example, what I'm doing, I'm revisiting that calculation, finding out what the covariance of the gradient noise is, plugging it into the expressions, right? And running a simulation and comparing the MSD to that expression. Okay, so that's what I'm carrying out in this example. It's just another example. You can read it. Okay, so it's similar in nature, not that different. Okay, this is case 3. Okay, so this is the covariance now. Okay. You are going to have a Pareto solution, and then I find an expression for the covariance in this case, okay, and then you can find out what the MSD is, okay, and then you can simulate the results and you will observe similar performance. Fine? Okay? So this brings me to the point I mentioned to you. Okay, why is it that for larger mu I see a bigger difference, right? And why is that the theoretical expression that I see, I have 2 levels, right? It's because of what I explained. This is exactly what this expression here is saying, okay? Higher order MSD, okay? So let me, okay? So this definition that we did before, okay, is only extracting the first order term in mu for the MSD, right? And that's exactly what we did. This is the MSD expression I derived in the theorem. If you use this expression, it depends on B through F, right? Different algorithms will have different B's, then you will see that the MSD will be different. And the simulation showed that, okay? However, if I now take this and use the low rank approximation, we are going to ignore this term, and what's left will be similar regardless of the algorithm, right? So to first order in mu, the algorithm should have the same performance. So if mu is very, very small, the performance would be the same. But if mu is larger, right, then this expression will show you these differences. That's what I'm trying to explain here, okay? Okay? Yes. No, I'm just telling you that how did I get the first order approximation? I replaced I minus f inverse by this term plus this term which I ignored. Okay? Yes, mu squared.
But if I use the trace j sub kx,
yes,
there is mu 1 plus gamma n.
That's okay, but what I'm saying is that this expression here, when mu is large, okay, when mu is I mean, not too large, but let's say 0.1 or 0.01 that I used, this mu squared term that I'm throwing away here will not be that small, right? Will not be that small. So if I keep it, I get a better approximation for the MSD than if I throw it away, okay? That explains the difference, okay? Very good. Remember these expressions here? That's what I'm referring to, okay? So I use these expressions, okay? These expressions, okay? Now, by the way, another way for you to find the MSD, okay, so now you have several ways to find the MSD. First order approximation, that beautiful expression which has P's, H's, and G's, right? That's what people usually would use, okay? But now if you want to be more precise, this is more precise, right? Okay? This or that, depending on which, right? Another way to compute it is compute the trace of that sum, right? That's another way, because that's x. Compute the trace of that sum, okay? Of course, you're not going to run the sum up to infinity. You run it up to a certain point, right? Because b to the n is going down to 0. B is stable, right? So you can compute few terms, add them up, the trace of that. If you don't want to compute, because why I'm saying this, okay? What are the sizes of the quantities involved here? You know, because each one of these f's is a block Kronecker product of a b with a b, and each b is a Kronecker product, right? Now, if you have a network with 100, even with 20 agents, do the calculation. Maybe that could be a homework problem. What's the size of this matrix, let's say, if I have a network of size 20, okay? It's a simple problem, just so that you get an idea, okay? So if this is a large matrix, inverting it can be a problem, right? So computing it through this sum up to can be another alternative, okay? Anyway, so I showed you where these differences come from, okay? So that's it, okay? So you can use either this form or that form. Fine? Okay. Now, what about the excess risk? I haven't talked about the excess risk. Well, the same thing, yes. Yes.
As you said before, there are situations we cannot always guarantee that the performance of the network will be better than that of the individual
yes.
agents when they are working alone. Can we set the weights in such a way that
right? This is next lecture. Next lecture, okay? For now, yes. For now, if the combination policy is doubly stochastic, there are examples that tell you that it's not always the case. In the next lecture, I'll ask this question: can I make it such that it's always the case? Right? Next lecture, okay? For now, let's continue. So the excess risk, okay? Right? The excess risk, I have to compute a weighted mean square error, okay? Where this h, if you remember, this h is the sum of the q bar h, not the sum of the qh. There is the q bar, which I normalize to add up to 1. That's all. Okay? If you repeat exactly the same calculations, I'm not going to go through this proof, very similar to what we did before, okay? You will get similar expressions. What's the difference? Here we had jx. Now we have qx. What's q? Again, all zeros, except at the corresponding location, you will have the h bar. Rather than I, you will have h bar. Okay? Because you need h, okay? And here you will have, before it was just x, here you will have block diagonal h with all h's. That's all, okay? Proof very similar to what I did before, okay? So I'm going to skip the proof. Even though you have them in the slides, I'm going to skip them, okay? And then if you simply, sorry, actually I don't have them here. This is the proof. No, I don't have, sorry, the proof is coming, okay? The proof is coming, but I'm going to skip it. Now, if you simplify the expression, following exactly what we did for the MSD, right? Okay. Right. Again, the traces that you need can be written like this. So the difference is JK is replaced by this QK, right? I is replaced by this H bar. That's all. Now I can repeat the same calculation here, right? Repeat the same calculation and you get this first order expression for the excess risk. Remember, the excess risk is measuring how much the global cost or risk is at in steady state is away from the best it can be on average, right? Expected value of J bar minus J bar at the estimate, J bar at the Pareto solution, right? And this is the expression. Okay, it looks a little bit simpler, okay? How simpler? You don't have HK here, right? Okay, because you don't have HK, this is simply a scalar. So you will only be left with trace of something that has G here. But you know, the trace of something, remember the G has RS transpose. So the trace of that, I can replace it by 2 times the trace of this R. That's why you end up having a factor, okay? This is how this expression was simplified relative to what you had before, okay? But this is the expression. That's why I write it in, I could have written it in terms of G. Trace of G here, but the trace of G is related to the 2 times the trace of R. So I'm writing it in, I couldn't do this in the MSD case because this appears first multiplied by a sum inverse of QH's, right? So I cannot do that in that case. Fine? And again I have, okay, I'm going to skip the proof. This is for the real case, okay, when H is 1. Okay, I'm going to skip the proof because very similar, okay? So the proof is skipped, okay? You can read it. And then I have a few examples, right? A few examples, okay? Again, if I apply this to consensus and diffusion, then the Q becomes mu P, right? If the mu is uniform, okay, this is how much excess risk you are going to get at every agent or on average. This is the performance, okay? So everything I did for the MSD, you can do for the excess risk. You see that the expressions are very similar, right? So I don't have to be repetitive. You get the idea, right? Otherwise, you will also be bored, right? Okay? And this is a simulation showing exactly the same behavior. Look, the difference between the step sizes, I explicitly wrote it here, 5 times that, right? And this is a simple example. I have 10 learners in this case. In this particular case, they are using the metropolis rule, one of the rules. You're going to see it. We saw it, I think, before. You're going to see it. Okay? So in this particular case, you can see again, this is, I'm plotting excess risk now. Consensus and diffusion, very close to the theory, very close to each other. You always see that little improvement there. Here I increase the mu, so now you start seeing more significant differences. Why? Because exactly of the approximation, right? You can find exactly what this horizontal theoretical line that would correspond to the black curve here, you can find it from the expression. Use the more accurate expression, okay? The red line is the non-cooperative case, okay? Right? The same kind of behavior. Okay? Again, this is another example. I'm just going to skip it, okay? This is diffusion, okay? I think this is, right? I'm just applying diffusion to solving a learning problem where you are trying to minimize a risk function, and the risk is the expected value of Q, for example, the logistic risk, right? Here I'm writing it in general. Okay, that Q could be related to the logistic function. This is how the diffusion learner will look like, correct? Okay. What would be the gradient noise? It is the difference between the gradient of the Q, because you are using here the loss function of the risk, the gradient of the risk function, times the gradient of the risk function. So this difference here, okay, is the gradient noise. In this particular case, the cost is the same across all agents. The risk is the same because it's not Q sub K, it's Q. The risk is the same, so the omega will be the omega 0 you are looking for, okay? at that omega 0, the gradient of the risk is 0. So your gradient noise is simply that first term, right? We did something like this before. Okay, so you can find what the covariance of the gradient noise is. It's just the expected value of that, right? The gradient of the loss at omega 0, and you put it down here, and you get the expression, okay? So for example, you can use this expression to find out what the excess risk is for logistic regression running over a network, right? How far the risk will be from the optimal value, right? And again, it will be proportional to mu. Okay, so you can pursue all of these. Here it is. You see, I then apply to this particular choice of Q, and I run a simulation. This is how the diffusion logistic regression will look like, whether you do it in ATC or CTA version. Okay, and then I have a simulation here, just to show you how well theory matches with simulation, right? The same. Okay, this is simulating a network that has 20 agents running diffusion logistic regression, right, to solve a pattern recognition problem, for example, how well the excess risk will be, right, and how well the theoretical expression matches that. Okay, and again, higher order terms. Okay, so the same thing I talked about for the MSD. You can use the more accurate expression, okay, to try to explain this difference, okay? So this parallels the MSD, okay? You can use this more accurate expression instead of the low rank approximation. Fine? Okay? So let's now show you how that lower part is indeed lower than the upper part in the learning curve corresponding, let's say, to consensus, right? You can show that analytically. Okay, so this is actually another example. So let's go through it quickly. Okay, again, I will not do all the calculations. They are all done in great detail in the notes, because by now you get the idea, right? So let's just do the calculations. Again, let's consider consensus and diffusion. Two of the A's are set to identity. The other A is set to A, right? Very good. Okay. So the first thing I would like to show you, for example, or what this example is showing you, is why diffusion outperforms consensus, right? And you saw it in the curves. But that simulation, let me show it now analytically, okay? We showed you before that because of the asymmetry in the consensus update, diffusion, right? Regardless of the topology, diffusion will always remain stable if the non-cooperative agents are stable. But that's not true for consensus. The network can grow unbounded, right? The state of the network can grow unbounded. So that's regarding stability. Now I'm going to show that the same asymmetry has an effect on performance. That's why you see that the performance is improved if you apply the diffusion strategy. Okay, so this is how. So this is an example. Let me show you an example here. So let's assume that all agents are using the same step size. So you have a network of homogeneous agents, right? They are all using similar step sizes. That's what this means, and this is a reasonable assumption, okay? In the mean square error case, okay, I have that the Hessian matrix is the RU. So I'm assuming that all of them are observing data also that arise from the same distribution, okay, from the same distribution. Okay, so this is an example over MSE networks, okay? So you know what this H is. This H is RU transpose. In the real case, it's 2RU, okay? Okay, what about gradient noise, right? What about gradient noise? Okay, remember that gradient noise in the mean square error case is what? Is sigma vk squared, you see RSK is sigma vk squared times something like this, RU, right? Right? I'm assuming RU is uniform here, okay? So when you define your G, you will get this sigma k squared multiplying RU transpose something, right? So here I'm just saying, let's assume that this GK is indeed a multiple of some matrix G. So I'm calling this G, right? That's all. I'm writing it more generally like that. Some multiple of G. I know what G is in the mean square error case, okay? Okay, so I'm calling this G, okay? Very good, okay? Here I'm just reminding you, you see, remember that I told you what this is, right? So I may have forgotten a factor of, you get the idea, okay, that this is what it should be, okay? So the Haitian is 2RU. I think this is the real, I'm doing the real case in this example. I think I'm doing the real case, okay? Do I say that somewhere? Yeah, real data, okay? So that's why the Haitian is 2RU, and that's why you get this 4 here, okay? But you get the idea. So this G, this constant G in this case would be 4RU, right? The important thing is I know H, I know G, fine? Okay, so now, what do I do, okay? So let's introduce this matrix here, RV. This is just, I'm just introducing a new matrix. I collect all the noises into this diagonal matrix, okay, RV, the power of the V's, okay? Because remember, what was, okay, that matrix S, this matrix S, what was it? It was A2 transpose M, right? Sorry, no. This S was the diagonal with the G's, right? But I'm assuming that each G now is sigma V1 squared, correct? Some constant G. Sigma V2 squared, some constant G, right? So that's simply this diagonal matrix Kronecker G. That's all, okay? But I know it, okay? I'm just telling you, okay. Now, I want to find the MSD for the distributed solution. But now I want to see the differences. I will not take the first order approximation because I'm not going to see any differences there, right? The first order approximation, the expression is the same regardless of A. So I have to use the more accurate expression, right? I'm going to use the expression written in the series form. I could have used the other expression, right? Written in terms of B vec of Y, I minus F inverse something, right? You understand? Because I want to see the differences. So I'm going to use this more accurate form. Okay, now, I know what Y is for each of the algorithms because this Y is defined in terms of A2, M, S, right? I know what B is. So Y and B are algorithm dependent, right? So this expression will bring out this dependency and tell me how they compare, correct? Okay. So here it is. I know what the B's are for non-cooperative, consensus, ATC, CTA. I know what the Y is for non-cooperative, consensus, ATC, CTA. Okay, I just wrote them down. Okay, fine so far? Okay, this is just algebra. Okay, okay, very good. This is just a little detail. This is not very important for what I'm talking about here. This is just to show you that for this particular case, because B of diffusion is the Kronecker product of A with that, then rho of diffusion, right, will be rho of A, which is 1, times rho of this, right? So in this particular case, diffusion, for this example, constant mu, but it's not always the case, right? For this example, right, the convergence rate in this case are the same. I mean, the spectral radius are the same, okay? And for consensus, you can just show, okay? Because what is the spectral radius for the non-cooperative case, okay? The non-cooperative case, this B is I minus MR, correct? Okay, so it's the maximum of this, correct? Because R is H, right? Constant, you see, I minus MR is block diagonal with constant blocks, I minus mu H. The maximum of this, correct? But you see, A has an eigenvalue at 1, right? A has an eigenvalue at 1. So I can say that this maximum is definitely smaller or equal to that maximum. Okay? Why? Because 1 is a possibility here, right? So this, the maximum over the eigenvalues of A, this maximum is either larger or at least equal to that maximum, because 1 is one of them. You understand? Okay, and this is, we showed before, that this expression here is nothing but the eigenvalues of the consensus matrix, and therefore this is the spectral radius of consensus. Okay, so this initial argument is to show you that actually in this particular case, the non-cooperative solution has faster convergence than the consensus solution. You can see it here, okay? I'm more interested in the MSD expressions, okay? So let's now compare the MSD expressions, okay? Why? Because for the convergence rates, mu is very, very, very small. So I minus mu h, for all practical purposes, they all will be very close to 1. So you will not see that in the convergence rate. But in the MSD, you saw in the simulations, the convergence rates were always technically similar, even though the theory tells you that one has to be a little bit better than the other. But you don't see it because mu is very small, and 1 minus mu times that, okay, it doesn't make a difference. But for the MSD, it makes a difference. So let's do this calculation. So here I'm going to do the calculations in closed form, so I'm going to assume that my A is symmetric, okay? My A is symmetric, which means A is doubly stochastic in this case, okay? Just to keep the calculations. In one of the references, we do it in a more general case, okay? If A is symmetric, also it's diagonalizable, right? Okay? Now look what I'm going to do. If A is symmetric, it's diagonalizable. X is the vector of eigenvectors, D is the eigenvalues of A, right? So you can see here, if I bring this X to this side, so the columns of X are right eigenvectors, the rows of X inverse are left eigenvectors. That's what the columns and rows of X and X inverse are, right? Right and left eigenvectors. Okay, since X inverse is identity, obviously the columns of X, the rows of X inverse are orthogonal to each other. I can normalize the columns of X to be always equal to 1 in norm. Correct? Okay, I'm just writing down an eigendecomposition here, okay? So these conditions will be satisfied. If I multiply any column of X by A, I get back that column. Any row of X inverse by A, I get back that, right? Up to eigenvalue. Okay, so under these results, look what will happen. Okay, so I normalize the X's to add up to 1. The X's are orthogonal to each other, okay? Because this is a symmetric matrix, right? This is a symmetric matrix, okay? So this is what I want to show analytically, that the ATC diffusion, its performance is always superior by a little bit to CTA, which is of course always superior to non-cooperative, so that's number 1. And number 2, ATC is always superior to consensus, right? So this explains once I prove this, I explain that curve, okay? But you see, I haven't compared CTA with consensus because this can be this way or that way. But ATC always is better, okay? And moreover, if your step size lies in this range, okay, mu lambda min of H between 1 and 2, okay, then consensus is the worst. Even in comparison to the non-cooperative solution. It cannot beat the non-cooperative solution. Okay? So how do I prove these results? Okay, this is how I prove these results. I'm not going to do all of the algebra here, but to show you the idea, okay? First of all, I introduce the eigendecomposition of the Hessian matrix. Remember, I'm assuming in this example all Hessian matrices are uniform. So these are the column, lambda of H are the eigenvalues, okay? And I introduce the eigenvalues of A, lambda m of A, and the eigenvectors of A, x and y. Now, what do? You come back to this expression here. Okay, this is some algebra you have to do. You come back to this expression. Remember, Y has A in it, B has A in it, right? And they have H's in them. Replace these A's and these H's by the eigenvector decompositions. Okay? And remember, some of these eigenvectors will be orthogonal to each other. Some of them will have norm 1, right? When you do these calculations, you will find that expression simplifies to these expressions, okay? This is just algebra, okay? I'm skipping it. This is a homework problem. Show that this follows from that, okay? It's one of your homework problems. It's just simple algebra. But let's look at the expressions, okay? This is what you get from the MSD expression we derived, not the first order approximation, the general one. Let's look at this expression, and it already tells you the story. You see, look at let's compare first ATC to CTA. To CTA. Okay? The multiplying factor is the same for all of them, correct? Here in the numerator you see y, this is the norm of the right eigenvector y, the norm of the eigenvector of h. You see it is the same in all of them, correct? But you see, for ATC it appears multiplied by an eigenvalue of a. And all eigenvalues of a have magnitude less than or equal to 1, correct? This is not here. So right away you see the MSD of ATC will always be superior by that, right? Okay. Let's compare now with consensus. Okay? By the way, you can compare with non-cooperative and the same conclusion will hold, because the numerator here is always smaller and the denominator here will be larger, because you are subtracting something that's smaller. Okay. Now, what about ATC and consensus? Okay. Here you have to do some algebra, right? What algebra? You can do the following. Take this term minus this term. What do you expect to get for the conclusion to be correct? Negative. So that's what the algebra will show you. Simple algebra. If the condition on mu, I told you before, 1 less than mu, lambda min of h less than 2, holds, then if you subtract this from that, term by term, I mean, what do you expect to get? Positive. Okay. So that's exactly the algebra that you can do. Okay. That's the algebra that you can do. Okay. So when you put together these results, okay, so I'm going to illustrate it for an example here. You see, this is the same example, uniform h, uniform mu. Let's illustrate these conditions graphically. Okay. For this example, I just wrote down what the expressions are. Okay. This is what you get. You get something like this. What these results show you, okay, here I applied the results to a special case, okay, to this case, uniform mu, and the h is this, so it's just a multiple of the identity. Just make it simple, okay? Plug it back into the expressions. They simplify to these expressions, okay? Now, this is for the case of 2 nodes, okay? This is for the case where I have 2 nodes only. One uses A, 1 minus A, the other uses B, 1 minus B, something like that, okay? Okay. So for this example, you can arrive at this conclusion. So you have a coefficient matrix which is 2 by 2, right? It has A, 1 minus A, something like this, 1 minus B, B, right? Okay. So A and B lie between 0 and 1. So you can divide that square into areas, okay? First of all, this expression will allow you to conclude that the MSD of ATC is better than any other algorithm throughout this rectangle. Anywhere you choose A and B in this rectangle, so you see I have 3 regions here. 3 below this line, 2 between this line and that line, and the 3rd region above this line. And there is actually a 4th region above the dotted line. You can show in all 3 regions, ATC is the best. Okay. You can show above the dotted region, consensus is always unstable. And we showed this before. There is a region, diffusion will always be stable, but there is a region where consensus becomes unstable. That's the dotted region up here, okay? This region, I tell you the equation of the lines, okay? And now, in region 2, CTA is better than consensus. In region 1, below the blue line, consensus is better than CTA, okay? So these results, okay, tell you why, right? You see the curves that you saw before, okay? Why the diffusion always converges to a lower level, okay? Consensus and CTA, they are in general very close to each other, but ATC will always do better because of these results, okay? You understand this example? Yes.
Do those red circles are supposed to be something?
Yes, that's red, that's danger, right? Okay, okay, danger. Okay, you shouldn't come close to this area, okay, for consensus. Diffusion, it's okay. There, I say there, consensus unstable in this region. I know you don't have the circles in the book. I added them here, right? Okay, so, I just have the dotted line in the book, but then, right, okay. The circles just to mean that area has danger in it. Anyway, you get the point, right? Okay. So this is the same example, okay? Anyway, the last example is just to show, okay, you see here, this is the expressions for the MSD that come from the more accurate MSD expression, right? Okay. One of them is linear in mu, the other is higher order in mu, okay? Okay, because you see here you have mu squared multiplying all of them, correct? Look here. If mu is very, very small, when you expand this term here, sorry, let's expand this term, okay? What will you get? In the numerator, the 1 will cancel out, right? You will get mu and mu squared in the numerator, right? One of those mu's cancel this mu, okay, right? So you end up with a constant minus a mu in the denominator. That mu becomes very small compared to the constant. So this first term will end up giving you the first order term approximation we had before. This other term here will be higher order in mu. That's what this example, this last example in these notes is showing you, that if you go to this example, okay, if you go to that example and you massage that first order term, you see I already eliminated the 1 from the denominator, okay? And one of these mu's is going to cancel one of these mu's. And then because this is a small, it's going to cancel the 4. If you work out the expression, you get exactly what we used to have before. This is just to tie things together, okay? That this expression indeed, up to first order in mu, it is the expression I had before, right? Okay? Fine. So what I did today, right, I completed the derivation of the performance expression for the network, right? First order approximation in mu, and then I also told you a more accurate expression that you can use if you are interested in bringing out the differences between the algorithms, right? And then I showed you several examples to illustrate that behavior, and you saw that there was indeed a good match between theory and practice. Fine? Okay? So that concludes this lecture. And then next time, what I'm going to do, I'm going to use this expression to answer now, start answering some interesting questions, like the question that he asked. Since the distributed solution, on average, beats the non-cooperative solution, but not necessarily on an individual basis, can I choose the A in such a way that I can make it perform better than every individual non-cooperative agent? This is one question. There are other questions that we will answer starting next time. Yes?
You showed an example where the WKs are different.
Yes.
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 So if they're highly different, does it make sense to cooperate because the network as a whole will converge to one W star?
Yes.
Which will be different from all the W.
Yes, that's true. That's a good question. Yeah. Here in this particular course, I'm talking about this situation where the agents are interested in cooperating and converging to a common solution, right? But there are variations, and I can give you references. You can find some of them also on my website, where we have studied problems where different clusters of the network, we refer to those as multitask diffusion problems, where different clusters of the networks may be interested in converging to different weight vectors because that's their interest, right? So, so an algorithm like that will make different portions of the network converge to different W's, not necessarily to the same W. And then you can assess how well each one of these clusters is going to get close to its own W by deriving similar expressions to this, right? In the works that we have done it only for the mean square error case, but you can do it more generally like this.